Okay.
Okay, so I'm going to continue talking about angle trisection today, kind of investigate different properties that come with constructible and trisectable angles. So outline my presentation. I'm just going to give a recap of background from what I talked about last time, then get into classifying angles of integer values and which angles are constructible and which are trisectable, and then go on to talking about angles with rational cosines and tangents. So from last time, we talked about the different constructions that we can do with the just ruler and compass. So that involves we can draw a straight line from any point A to B. We can extend any segment into infinite, or we can extend any line segment, and we can make a circle with a given center and radius. We also talked about last time when a number is constructible, so it can be constructed with the ruler and compass in a finite number of steps. So given constructible lengths of alpha and beta, we can construct alpha times beta, alpha divided by beta, and also square roots. So it'll be important in remembering that. Last time we talked about the impossibility of trisection, so we can't trisect an arbitrary angle. We showed this by example by proving that we can't trisect a 60-degree angle. And that came from this cubic right here. We showed that that has no rational roots. When theta equals 20, that 60-degree angle is not trisectable. So that's kind of just background from last presentation. And using some of the information we talked about last time, we can then kind of classify which angle values of integer value we can construct. So we know that a 20-degree angle is not trisectable. We know we can copy a given angle, and we know we can bisect a given angle. I showed the construction of that last time. And so this information here will eventually tell us that the smallest integer angle that we can construct is a 3-degree angle. So what we need to start with is we need to start with an important theorem that says if k is a positive integer that divides 20, then we can't construct an angle of k degrees. So this makes sense because let's suppose there's an integer n such that 20 equals mk. Then since we can copy angles, if we had a k-degree angle, we could just copy that n times, and that would give us a 20-degree angle, which we know we can't construct. So this is important because it tells us that we can't construct a 10-degree angle, a 5-degree angle, a 4-degree angle, 2-degree angle, and most importantly a 1-degree angle. And that makes sense because if we could construct a 1-degree angle, we could construct an angle of any integer degree value. So using that information, or I'm going to talk about first, I guess, a side note theorem that says an angle theta is constructible if and only if cosine theta is constructible. So here on the left side, we start by assuming that if an angle theta is constructible, and so and we know we can construct a segment of unit length, and so then we can construct a perpendicular bisector or a perpendicular line, and then this value down here is cosine theta. Now, if we assume that we can construct cosine theta, then we can construct a perpendicular line on the right endpoint, and then using the left endpoint as the center of a circle radius 1, we can draw an arc there, and where those intersect, we get a line segment length 1, and thus we've constructed this angle theta. So basically, if we can construct an angle theta, we can construct cosine theta and vice versa. So that'll be important when we're talking about which angles we can construct. So this is kind of an outline of how we can come to construct a 3-degree angle. And you can do this in multiple different ways, but this is the way I chose. So we're going to start by proving that cosine of 36 is constructible, which then implies that a 36-degree angle is constructible. And from last time, I proved that we can trisect a 90-degree angle. So that means that we can construct a 30-degree angle. And since we can copy line segment or angles, we can subtract them, which is basically just copying the smaller angle instead of a larger angle to get this 6-degree angle. And then we can bisect that to get a 3-degree angle. So it's kind of a lot of steps that eventually get us our 3-degree angle. So what I'm going to basically show is prove that the cosine of 36 is constructible. So if we start with an angle 36 degrees, this is a 36, 72, 72 triangle with side lengths 1 and base x. Then if we bisect this 72-degree angle, we get a 36-degree angle. And that gives us another isosceles triangle right here. So this dashed line is also x. And then we also have this is an isosceles triangle, which which gives us x here, and 1 minus x here. Okay, so this is just a figure from before. And we can use similar triangles to do 1 minus x, which is the base of the smaller triangle, over the base of the larger triangle here, equal to the side of the smaller triangle over the side of the larger triangle. And then we can get the quadratic equation and use the quadratic formula to get our root, and we can only use the positive one because that's the one that makes sense. And using the law of cosines, we get x squared equals 1 plus 1 minus 2 cosine 36. And substituting this into that equation, we get that cosine of 36 is equal to 1 plus square root of 4, square root of 5 over 4, which we know is constructible because it's equal to a rational plus a rational times the square root. And so this is actually, cosine of 36 is actually phi over 2, where phi is equal to 1 plus square root of 5 over 2, which is the golden ratio. So it's interesting that that, again, appears here. And yeah, so we've shown what cosine of 36 is. And also interesting is cosine of 36 is cosine of pi over 5. And as you remember, when we learned all those trig values, cosine of pi over 3, pi over 4, pi over 6, we never knew what cosine of pi over 5 was, and we never learned that. So that shows up here.